I just got off a red-eye flight, and so I don't have much energy, but I thought I'd do a quick post on free energy before I dive into things in the lab. So, hope it helps. Imagine you're in a room full of couches, and you're trying to decide if you want to change which couch you're sitting in. It's going to depend on a few things that you'll think about before you decide whether it's worth it to move to that new couch. So one of these things is how much room do you have to spread out? So this is like the entropy term for molecules. So molecules like to be spread out, and so you'll have higher entropy if molecules can spread out more. So if you have if you break a molecule into smaller molecules, then you have more molecules that can fly around, which has more freedom than if you have like one big stuck together molecule. Similarly, when you have, even if you don't break a molecule, if you give it some more like flexibility, like you can think of entropy as how many states that a molecule could be in. So by states, you can just think of like either being in different places or in different kind of like shapes, not really shapes, but just like bond angles and that sort of thing, and just wiggliness. So if you imagine like you had your arm free versus your arm in a sling, you can take on a lot more states, so you can do a lot more like different movements and stuff if your arm is free versus when it's in a sling. So molecules like higher entropy. So keep that in mind. Okay, how about enthalpy? So you can think of this as kind of like how comfortable the molecule is. So enthalpy is heat. So heat is like the energy of the molecules. So if you're on a really uncomfortable couch, you're going to be squirming around a lot, and so that's not very comfortable. But if you have a comfy couch, then you can relax more. And so molecules like having when you have a bond, so basically if a bond has a high enthalpy, that means that it takes a lot of energy to break it because the molecules are really, really comfy there. So if you have a high enthalpy, it's going to take a lot of energy. The molecules are really comfy. It's going to take a lot of energy to break it. So it takes energy to break bonds in the enthalpy term. But on the other side, if you form the bonds, then you release the energy that you get when you break it. So it's like energy can't be created or destroyed when you think about this whole like universe level, the systems level. So the energy that it takes to break the bond is the same amount of energy that it takes to make the bond. So for a really strong bond, it's going to have a high enthalpy, meaning that it's going to take a lot of energy to break it, but when you make it, you're also going to get a lot of energy. And then the final thing to keep in mind is the temperature. So the temperature is kind of like a modulating factor. So it's not going to change the entropy or the enthalpy, but it'll change how much we care about the different ones. So it's kind of like when you're doing that couch hopping, like if it's hot out, you're going to care more about spreading out than cushiness. So it's like it's tipping the scale in the favor of one or the other. And then ultimately these go together to make whether or not it's worth it for you. And so if it's worth it, so if you're better off in the new couch, that means that you have a negative free energy, so a negative Gibbs free energy, so a negative delta G. So delta is just is that triangle thing, and it means it's changing. So if you have a negative delta G, that means that the reaction is what we call spontaneous, and it's like a favorable reaction. But just because it's favorable doesn't mean it's going to happen. And so one of the factors that's going to determine whether it happens is something called the activation energy. So basically, like, are you too lazy to get off that couch? If you're too lazy to get off the couch, it doesn't matter if you'd be happier in the other couch, because you don't have the activation energy to go move to that other couch. So we can put all these terms together to get this equation for Gibbs free energy. So remember, a negative Gibbs free energy means a reaction is spontaneous. And a negative delta G, means it's exergonic, so it releases energy. A positive delta G is non-spontaneous, so it takes energy, and it's what we call endergonic. So endergonic means we take energy, exergonic means you release energy. And you can think of it kind of like it takes more energy to be in an uncomfortable couch than it does to be in your comfy state. So when you're at your comfiest state, you're just all like relaxed, and so you're chill. But when you're so you had released the energy that you would have had when you were like flying all around the place. And so its formula is delta H, so the change in enthalpy. So this is whether it will give off heat. So if it gives off heat, so if you have a negative delta G, that means that it's exothermic, it's releasing heat. So it's negative because you're thinking about the end point. So you're thinking that you're releasing heat into the system, or you're releasing heat into the universe, so the system, so the thing that you are, like, that the reaction is happening in is losing heat. Then if it's positive, that means it's endothermic, so it takes heat. So exo is release, endo is taken. Okay, so that's going to be your delta H term. You can think remember we want delta G to be negative in order to have spontaneity. So if you have a negative delta H, so an exothermic reaction is more favorable if you don't compared to an endothermic reaction, but we still have to look at the other half of the equation. So we have this minus T delta S, and so T is the temperature, and it's in Kelvin units, so be careful with that. And then delta S is the change in the entropy. So do the products have more freedom than the reactants? And so here we're subtracting. So to make the number smaller, we want delta S to be highly positive. So we want more freedom in the reactants for them to be happier. So you're happier if you have more stable bonds and more freedom. But, so if you have negative delta G, that means spontaneous, but non-spontaneous does not mean impossible. So if you think of a ball at the, you could think of like a bowling ball at the top of a ramp. And at the top you have the energy of the reactants, and the bottom the energy of the products, and then the delta G is the change in energy. The ball will fall down from the top on its own, so that would be like a spontaneous reaction. But you can also push the ball back up. It's not going to go up on its own, but you can push it back up. And so non-spontaneous reactions can happen if you give them energy to go. And spontaneous does not mean likely. So when you're looking at that ball on the ramp, what you're not seeing is that there's a barrier. So you can't just fall right down the ramp. Instead, you have to go up and over a transition state, and it takes activation energy to reach that transition state. So that's like when we were talking about being too lazy to get up off your couch to move to a new couch. So in biochemistry, often reactions are made possible by molecules called enzymes, which are often proteins, sometimes proteins and RNA complexes, or just RNA. And what they do is they lower the activation energy that's needed for the reaction to occur. So we can get reactions to be more likely to happen by adding an enzyme to act as a catalyst to lower that activation energy. But enzymes are specific for the various reactions, so it's not like you could just add any enzyme to any reaction. But if you add the relevant enzyme to lower the activation energy, or you couple it to another reaction if it's endergonic, so if it needs energy to proceed. If you couple it to another reaction that's exergonic, so that releases energy, then the one that releases energy can give it to the one that needs the energy. And so just a little more on this. So for enzymes, what you can think of it as kind of like this rainbow. And so if you're trying to break a stick, you have to bend the stick to a really awkward point before it'll actually break. And so that awkward point is kind of like the transition state. So the activation energy is what's required to reach that transition state. And the enzyme's going to make that lower. So I have a lot of other posts on enzymes if you're interested in those. But let's get back to Gibbs free energy for now. So we can't predict whether a reaction will occur because spontaneous does not mean that it will occur, remember. Spontaneous does also not mean anything about how fast the reaction will occur. That depends on kinetic stuff, which we're not getting into here. And we're just dealing with thermodynamics here. So this is dealing with systems like, the like end game, basically. So if you let all these chemicals do their thing, where will they end up eventually? So we can predict if a reaction will be spontaneous if we know, if we use that equation and we know how the entropy and the enthalpy of the products and the reactants differ. So the reactants are what we start with, the products are what we end up with. So going back to our couch analogy, we have the entropy. So that's going to be represented by the S term. That's how many, so if you lie on a couch, sit on a couch, stand on a couch, so that's where you have your molecules that have more different ways you can find them. Then enthalpy, that's the heat. So that's the energy of those bonds. So the higher the enthalpy, the stronger the bonds, the more energy it's going to take to break the bonds, and the more energy that you'll get when you make the bonds. And then the temperature is going to kind of help push things one way or the other. So a reaction that has a negative enthalpy and a negative entropy is going to be spontaneous only at low temperatures. If it has a negative enthalpy and a positive entropy, it's always going to be spontaneous. Because remember, we have delta H minus T delta S. So if we have, conversely, if you have that switch, so if you have a positive enthalpy and a negative entropy, you're never going to be spontaneous. And if you have a positive both, then it's only going to be spontaneous at the higher temperatures. And so we can look at this more in a more formal chart that you can find on the blog post, as well as some help for figuring out when a reaction will be what. But before I finish this, I just want to give a little reminder that we have to deal with the laws of thermodynamics. And so sometimes it can seem really kind of confusing when we're talking about losing and gaining energy. The basics is that we're talking about things at different scales. And so when a reaction is losing energy, it's not like that energy is just disappearing into nothingness. That energy is being gained by the system. So, or by the surroundings. So the universe is staying constant. You have your system where things are happening, and the surroundings, which is around the system. If your system is losing energy, the surroundings are gaining energy. If the system is taking energy, then the surroundings are losing energy. And so the universe is staying constant this whole time. So that's the first law of thermodynamics. Energy can't be created or destroyed. It can only change forms and or move. And the second law of thermodynamics is that nature likes randomness and disorder. And so increasing entropy of the universe is favorable. And so this goes back to our entropy. So entropy is good, basically, is the second law of thermodynamics. You can see just a couple of examples. So before I talked about how spontaneous does not always mean likely or instantaneous. So you can see this with fireworks. So we have the coupled reaction here. The reason why fireworks, the overall is really exergonic. So it's going to release a lot of energy in the form of light and heat. But it's actually two separate reactions that are coupled, at least in the like the classical firework chemistry. And this is why it doesn't just like spontaneously or like burst. Your fireworks don't like instantly just like explode, because there's these two steps. And the first step is endergonic, so you have to provide energy. But then once you get that reaction going, it's exergonic, and so it's going to release energy, and it's going to keep the reaction going. You can also another example is an instant cold pack. So this one's interesting because it is exergonic, so it releases energy, but it's endothermic, meaning that it takes in heat from the surroundings. And the reason why it's able to do this is because it takes the heat to break some bonds. So you have to break the bonds of this like ammonium nitrate, and then it's released into the water to dissolve, so you have to break the water bonds, but then you make bonds between the nitrate and the water. So remember, if you have to add energy to break bonds, but then you gain energy when you make bonds. But in this case, you gain less energy than you use, or you gain less like enthalpy than you use, but you're gaining entropy because you're like you take that solid thing in that water network and you just like mix them up, so you get a lot more entropy. And so you have this reaction in which you're exergonic, so overall you are releasing energy in the free energy form, like in the free energy context because of the entropy, but you are requiring heat to make it happen. And so when you're taking in heat from the surroundings, you're decreasing the temperature of the surroundings, and so that's why the surroundings then feel cold. So those were the main things that I wanted to talk about here. It's obviously more complicated than couch shopping, but hopefully that analogy will help you just like get started with understanding.